Bueno, ya ahora sí, perdón. Esta presentación va a ser en inglés. Okay. Hello, everyone. Good morning and welcome to this presentation. Also, a warm welcome to those joining us via live stream. My name is Laura Rojas. I am the coordinator of the final graduation projects for the bachelor's degree in engineering physics. Today, we want to welcome Natalia, who will present her project titled Characterization of Quantum Light Sources Based on Self-Assembled Semiconductor Quantum Dots. This work was supervised by Ricardo Solano Piedra with collaboration of Denis Murillo Salazar. Also, this project was carried out at the Institute of Physics and Astronomy Division of Solid State Physics, Technik Universitat Berlin. I'm sorry if I mispronounce that. I will now explain the structure of this presentation. First, Natalia will present her work with a maximum of 20 minutes. Afterwards, the audience will have 8 to 10 minutes to ask questions and make comments. Also, the virtual audience, our guests from Germany, are welcome to ask questions. Following this, the committee will proceed with the evaluation of the student, and we kindly ask the audience to remain silent during this process. The examining committee is composed of Juan Carlos Lobo and Natalia Murillo. Each examiner will have up to 10 minutes to ask their questions and listen to the students' responses. Once this stage concludes, the audience will be asked to briefly leave the room so the committee may deliberate and assign the final grade. Finally, the audience will be invited back in so that the committee may announce the result, thereby concluding this defense. Also, I would like to clarify that the questions that will be held here in the auditorium will be in Spanish for Natalia, and she may answer in Spanish as well. Now we will begin.
Okay. Well, good morning, professors, everyone on the transmission. Thank you all for being here. My name is Natalia Quesada, and I'll be presenting my final graduation project titled Characterization of Quantum Light Sources Based on Self-Assembled Semiconductor Quantum Dots. As my professor said, which I carried out at the Institute of Physics and Astronomy of Technische Universität Berlin. So these are the main contents that we'll be seeing throughout this presentation. And first, we'll begin with the context and why this subject is so important. So the concept of a global quantum internet has emerged as one of today's major technological frontiers. It offers communication that's secure in a way that it relies on the laws of quantum physics themselves. And so if someone intercepts that communication, you'll immediately notice. And the technology that allows this is also the base for photonic quantum processors and future quantum computers. Now, what's the technology that's behind all this? These are single photon sources. Now, semiconductor quantum dots are promising because they behave like artificial atoms. When excited by a laser, they emit photons one at a time. And if we combine them with special photonic structures, such as circular Bragg gratings or CBGs, which I'll describe later, we can make more of those photons go into our detectors. However, these sources are still a work in progress and they still face some challenges, which is why we need to study and evaluate how they currently perform and to identify their limitations that affect their suitability in quantum communications. Now, that's why with this project, the main goal was to characterize these single photon quantum light sources based on self-assembled semiconductor quantum dots using optical and quantum optical measurements to evaluate their performance and their suitability for quantum communication systems. For this, I defined 3 specific objectives. First was to acquire and analyze the optical emission spectra of the sources using high-resolution spectrometry to assess their viability through power and polarization series with a report on spectral clarity, stability, and isolation. Second was to quantify their photon extraction efficiency through calibrated photoluminescence measurements to assess their brightness with a supporting statistical analysis. And third was to evaluate their quantum optical performance via time correlation measurements, extracting G2 values to assess their purity and determine their suitability for quantum communications. Now we'll see some of the theory of what's happening in the background. In the small scale, when a laser excites the material in a quantum dot, it creates charge carriers, which are bound pairs of an electron in the conduction band and a hole in the valence band. Then these carriers quickly relax from the superficial wetting layer all the way down to the S shell. The time this takes is the relaxation decay time. And then the final decay from the S shell down to the ground state is the radiative decay. And this is where the photon is emitted. Now for this, in our case, we used a pulse laser, which excited the quantum dots every 12.5 nanoseconds. And after each pulse, the probability of the dot emitting a photon decreased exponentially with time. Now, depending on how many carriers the dot captures, different excitonic complexes can be formed. Here we see examples of the lowest excitonic transitions, which are the neutral and charged excitons and the biexciton. Now, each of these transitions emits at slightly different wavelengths. So that's why we need to identify them in order to correctly interpret our measurements. Now, to study these processes, we use different optical measurements. First, we have microphotoluminescence or micro-PL spectroscopy. This gives us the emission spectrum of the emission, which shows us how sharp and isolated and clear each line is. And with some analysis, we can identify which transitions are present in the spectrum. Then with time-resolved PL measurements, we can study the radiative and relaxation decay times. Then with measurements made with Hamburg-Brown twist interferometry, we can get the second-order correlation function G2, which gives us the probability of the dot emitting more than one photon at a time. So a value of G2 of 0 means ideal, means true single photon emission. So we aim for values as low as possible, which translates to single photon purities as high as possible. Another important concept here is the photon extraction efficiency. This tells us the fraction of the photons that make it out of the device and into the detector. And here is where circular Bragg gratings become important. These are structures that are built around the quantum dot in a way that the dot is embedded inside this central mesa. And these structures act like a funnel, which shapes and redirects the emission in a way that more photons are emitted upward instead of getting lost inside the material. Now we're getting into the actual methods we used. But before we get into the measurements, we need to know what it is we're measuring. So here to the left, you can see an optical microscope image of the sample, which is an approximately 4 by 4 millimeter chip. And to the right, you can see a diagram of the layer structure. We begin with a gallium arsenide wafer, then 2 buffer layers, and then we have 24 pairs of aluminum arsenide and gallium arsenide layers that form what's called a distributed Bragg reflector, or DBR, which is a mirror that reflects light very efficiently at the emission wavelength of the quantum dots. And then we have the important part, the active layer, which is a layer of indium arsenide that begins with a wetting layer and on top of which the quantum dots are randomly grown. And this is between 2 layers of gallium arsenide. Now, this sample contained 3 types of CBG structures, CBGs 1, 2, and 3. In total, we had 61 structures across all three types. And as you can see from these SEM images, they vary slightly in design parameters, mainly in the central mesodiameters and in the ring and gap widths. Now, to quantify how well these devices perform, like I said, we use the photon extraction efficiency, which we calculate using this equation. We get the detected photon count rate divided by the optical setup efficiency, which I'll explain in a minute, and the excitation frequency of the laser. Now, to make all the measurements, we used this optical setup. We begin with the pulsed laser at 80 megahertz, then the beam passes through a software-controlled filter wheel, and then part of the emission is sent to a power meter so we can monitor the excitation power. And this other beam splitter allows white light to enter the path. Then the laser and the white light go through a microscope objective that focuses the beam into the sample that is inside a cryostat. Here, some of the measurements were made at 4 Kelvin and others were made at 7.5 Kelvin. Then the emission from the sample retraces the path and part of it goes to a camera. And then the rest is sent through this beam splitter to this mirror. Then we go through a half wave plate, a linear polarizer, a 900-meter long pass filter, and then a lens that focuses the emission into the monochromator. Inside the monochromator, the light is dispersed by the mirrors and the grating, and then this adjustable mirror allows us to send the emission either to the CCD, where we record the spectra, or into the Hambry-Brown twist setup, where the beam goes through a fiber beam splitter, which is connected to two SNSPD channels. This is the detector. And the detection events are registered by the time-correlated single photon counting module. Now, as for the measurements, if we rotate the filter wheel, we get the power series. And if we rotate the half wave plate, we get polarization series. And both of these series give us information so that we can identify mainly the excitonic transitions that are present in the emissions. Now let's look at the results we got for one of the structures, which corresponds to the first objective. This is structure CE91. Here to the right, we can see its emission spectrum. We can see the different lines, which emit at slightly different wavelengths, with each corresponding to a different excitonic transition. Then here we can see the power series we got for this structure. We plot the intensity of each line against the excitation power, and the value m, which is a power exponent, tells us how each line grows with power. And this value and the behavior of each of these lines help us identify these excitonic transitions. Now here we can see the polarization series. In the first figure, we can see the energy deviation against the polarization angle, and to the right, we can see the corresponding intensities. Here, the FSS is the fine structure splitting, which is a small energy difference between two polarization components caused by slight asymmetries in the quantum dots. And the DLP is the degree of linear polarization of the emission. For identifying the complexes, for example, we recognize that the exciton and biexciton lines have relatively high FSS values, and they have opposite energy deviation directions. Also, in the circular plot, we can see that they're both approximately constant in their intensities, which looks very different from this. This is the, in this case, this is the positive biexciton line pair. These have lower FSS values, it's almost a straight line, and they have opposite linear polarizations. So I did this analysis for all of the structures, and first, before we can calculate their extraction efficiency, we need to get the setup efficiency. Here we remember the optical setup, And here we have the transmission efficiencies of all of the components in the setup. So we also include here the efficiency of the reflectivity of the gold mirror that's on the sample where we focus the laser for this part. So if we multiply all of the efficiencies of the components and normalize by the reflectivity of the gold mirror, we get a setup efficiency of 8.12%. And this value is typical for setups like this according to recent studies. Now, I was able to analyze a total of 23 structures across the 3 types of CBGs, and these are their extraction efficiencies. They ranged from about 2% to almost 20%. Now, according to previous simulations that were done in the group, these structures were expected to have efficiencies in the range of 70 to 80%, and our results are much lower than that. Now, this could be because of 2 reasons. First, it's the possibility that we have fluorescence intermittency or blinking, which is when a quantum dot emits a photon and then goes dark for a certain period of time. And another possibility could be recapture processes, where an extra carrier populates the shell, causing a second photon to be emitted. Now, for the quantum optical measurements that correspond to the third objective, I selected 3 structures, one of each CBG type, choosing the ones with a higher extraction efficiency. And these were the conditions for these measurements. For each structure, I selected certain spectral lines and measured them either in a non-resonant wetting layer excitation scheme or a quasi-resonant p-shell excitation scheme at these particular wavelengths. And each measurement was done at approximately 40, 70, and 100% of the saturation power of each line. And first, we have the results for the radiative lifetime. Here, we found that the radiative lifetimes ranged between 0.7 and 1.7 nanoseconds, which the higher values slightly exceed the expected values of 1 nanosecond for this type of quantum dot. Then we also found that with a non-resonant excitation scheme, the relaxation decay time grew very strongly with the excitation power, and that the radiative lifetime slightly decreased with growing excitation power. Also, we found that in a quasi-resonant excitation scheme, the relaxation and decay times both remained approximately constant. And all of this is consistent with the theory of the process of these decays. Then we have the results for the HBT measurements, which were only made for CBGs 1 and 3. Now, most of the measurements we made look like this, where we can see how the central peaks are higher and then they gradually decrease in both sides. And this is a signature of the blinking dynamics that I mentioned before. Also, we can see this pronounced peak in the center at 0 delay. And in this case, this part is characteristic of the recapture processes that I also mentioned. So with these measurements, we were able to qualitatively confirm that these are the 2 main culprits of the low extraction efficiencies. Only one of the measurements was the one that looked like this, where you can't see either blinking nor recapture processes. And if we see the results, this was the one structure with the highest single photon purity, which reached almost, 98.7%. The rest of the structures, which showed both blinking and recapture processes, averaged 87%, with the lowest being 83.1%. Now, these low photon purities could also be because of another certain process that goes on inside the quantum dot that somehow decreases this this purity. Now, in conclusion, we were able to do the optical and quantum optical characterization of the indium gallium arsenide quantum dots inside CVGs, identifying their excitonic states through power and polarization series, and we found extraction efficiencies of 2 to 20%, as well as single photon purities from 83 all the way to 98%. And we identified long lifetimes, blinking, and recapture processes as the main limits. Now, for the impact of this work, this gives the fabricators, the growers of the quantum dots, information on their quality so that they can develop improvements in future samples. We also help support the development of these super important quantum light sources, and we also strengthened the collaboration between TU Berlin and Tech by transferring experimental and analytical expertise. And moving forward, we would need to keep studying the indistinguishability, far field emission, fiber coupling, to keep developing this type of single photon source and potentially move to doped electrically contacted samples, which will very much increase their performance. And in the long term, we look to develop robust, repeatable single photon sources that are ready for real-world quantum communications. Finally, I'd like to thank everyone from the Heindel and Reitzenstein work groups, especially Professor Reitzenstein for receiving me, and Gain for helping me so much throughout this project. These are my references, and thank you all for your attention.
Me oigo, sí. Muchas gracias, Natalia. Thank you, Natalia, for this lovely presentation. I would give a couple of minutes to our guests in case they want to say something or ask something. Okay, just give me a minute to see if we can put you on the speaker. I will turn on my camera so you can see me.
Can start? Okay.
And see Natalia, but I think you're ready. Go ahead.
Okay. Yeah, so first of all, I would like to thank Natalia for the very nice presentation. It was a very nice and interesting summary of your talk, Natalia. And I would also like to mention that you performed an excellent job in our group. So it was a pleasure to have you on board here in Berlin. And the results are really, really nice and strong for this short period in which you were at TU Berlin. So congratulations for this big success.
Thank you.
My pleasure. Can I also ask a question? I believe I can, yes?
Yes, of course.
Just a question about the quantum dot properties. So you presented also these polarization resolved measurements
Yes.
in which you identify the exciton and bi-exciton in the sense that they have an antiphase behavior as a function of angle.
These?
Exactly this one, yes. So I don't know. I mean, it's clear for me, let's say, what is the reason for this, but maybe you can also explain the reason behind this antiphase behavior, if you know the reason, which we see here. Do you know where it comes from?
Well, so the exciton by exciton have lower fine structure splitting, which I believe would be because, well, since the fine structure splitting is the difference, the energy difference between the polarization components from the asymmetries in the quantum dots, and the exciton by exciton are some of the lower excitation, excitonic complexes. I believe these would be more sensitive to these asymmetries and probably show up more on these plots.
Yeah, but here in the plot we have seen there's this oscillation behavior, yeah, right?
Yes.
Between the exciton and the biexciton, and when the exciton goes up in energy, the biexciton goes down in energy. So the question would be, why do we have such a behavior? Um, if you could draw a level scheme, but I'm afraid this is not possible. One can probably see it, um, but
Well, we didn't go so deep into the the theory of why this really happens, but
mhm.
I would say it would be because um, maybe they are in some ways symmetric to each other, so they have opposite behaviors.
Yeah, so in the end, one would need to take a look at the level scheme actually to have a clear idea. But essentially, you have an energy difference between the biexciton and the ground state,
Hmm.
right? And in between, you have the exciton. And if the exciton energy increases, the difference between the exciton energy to the biexciton energy must get smaller for a given total energy.
Yes.
Yeah, so higher exciton energy means lower biexciton energy and vice versa for a given energy. That's why you have this antiphase behavior between exciton and biexciton.
Yes, so it's conserved.
Yeah, indeed. So energy is conserved and it's shared between exciton and biexciton. If one goes up, the other needs to go down. Maybe you can have a look at the level scheme afterwards. So it's quite nice and nicely seen in this level scheme.
Yeah, of course.
Okay.
Okay.
Um, on what else? Maybe one more question, maybe from my side, a brief one.
Mhm.
So unfortunately, I would say this extraction efficiency is lower than expected. So it was
Yes.
20% instead of 80%. Um, so can you again tell the possible reasons why it's so small?
Well, like I said, we identified that pretty much all of the structures but one had blinking and recapture processes. And
Mhm.
since the blinking makes the dot like go dark for a certain amount of time, this would mean that it's not emitting one photon for every laser pulse. So less photons are actually being emitted. So I believe that's why the efficiencies are so low.
Mhm. So this is certainly one of the reasons, very good. But there could also be at least one additional reason. So maybe you mentioned it. So
Uh,
how about the dependence of the dot position inside the
yes.
structure? Yes.
Yeah, actually, yeah, that was actually something else I studied about, that the position of the quantum dot inside the CVG could not be optimized in the center so that it's like perfectly emitting upwards, but it could instead be a little dephased,
Mhm.
either sideways or up or down, so that it's not optimizing the emission. And that's more of a fabrication part.
Indeed. So this is certainly also a reason for low efficiency. Maybe not in the upward direction, but because this is pretty much defined in the epitaxial process on a nanometer accuracy. But the lateral displacement, this can always happen. And this is a big issue in all of our devices. And we need to work on this in the future,
Yes.
uh, uh, gain essentially. Uh, but this is most probably part of the reason, let's say. Okay, Natalia, then thank you very much. And
Thank you.
good luck for the rest of the defense. Yes. So well
Thanks.
done so far, I would say. Thank you.
Thank you very much, Professor Stefan.
You're welcome.
Ah, ¿Cómo se pronuncia el nombre?
As again, no sé si. I don't know if
It's
you're good.
Seth wants to say something.
Yeah. So also Stefan pretty much covered it. Natalia did very good job. For a very short time, she learned a lot of new topics and also could finish all the objectives we planned to. So quite good job on your part as well.
Thank you.
And maybe one question for the fitting part, let's say.
Mhm.
So in the HBT results,
Yes.
yeah, so we see some of the the discrepancy between the fit and the raw data.
Uh-huh.
Can you explain a little bit more on that side on why is that, and maybe how do we do better for the fitting in the
Okay.
future?
Yes, of course. So you're talking about this little space that's between the okay. Be- between the raw data and the fit. And this would be because of okay, well actually I have here this. So the software, the script that fits the data is based on these three functions. It's the instrument response function, which is the reaction time of the detector, the relaxation decay, and the radiative decay, which both I explained. But it doesn't take into account a second slow decay channel, which means that sometimes the charge carriers get trapped by a defect in the material, and they take a longer time to come back and get to emit the photon. So when that is not taken into account, which this is, well, this is a Gaussian distribution, and these three are exponential distributions. And since this one isn't taken into account, that's why we see that discrepancy. These are lifetime measurements. We can also see it here. And that's why we can see that also difference in the HBT measurements.
Yeah. Maybe for a little bit of correctness, I think it should be the addition, not the convolution, like on your
Yes.
part. Like, so
Okay.
it has to be added first, and then I think we convolute them later.
Yes.
Yeah.
Yeah, convolution.
Yeah. So yeah, nice.
Okay.
I think that's it for my part.
All right.
Thank you.
Thank you.
Okay, thank you very much for your participation. Now we will move on to our audience here in the auditorium. Does anyone has a question or a comment? ¿Alguien tiene? Ajá.
Hola Natalia, ¿todo bien?
Hola.
Ando un poquillo enferma, entonces por ahí. Muchas felicidades por el trabajo, súper lindo.
Gracias.
Yo tengo nada más una pequeña preguntita con las gráficas circulares y sinusoidales que tenías por ahí.
Ajá, estas.
Ajá, esas. Veo un más menos algo. ¿Cómo se obtuvo ese más menos?
Ok. Este más menos, bueno, vamos a ver. Esto se saca de estas series de, bueno, lo que obtenemos con una sola medición, digamos, es el espectro de emisión, la serie de potencia y la serie de polarización. Ahora, estas incertidumbres lo que tienen son varios componentes, digamos, que vienen desde incertidumbres de los instrumentos y también incertidumbres que vienen del tipo automáticas de los ajustes que se usan en el script. Entonces, eso las propaga y de ahí se saca esas incertidumbres. Sí, digamos, es básicamente la expandida de los diferentes ajustes que se usan para sacar pues, el ajuste, en este caso sinusoidal, de cada función.
Gracias, Natalia, y gracias a Marian por la pregunta. Ya estamos un poquito pasados de tiempo con las intervenciones, entonces vamos a proceder ahora con la evaluación del jurado. Now we're going to go ahead with the committee evaluation.
Ya estoy. Como yo no me oigo. Bueno, primero que felicitarte, el trabajo está muy completo y se ve que fue intenso cumplirlo en el tiempo que,
Sí.
que te propusiste, porque el semestre pasado estabas aquí recibiendo clases. Usualmente la gente para esto se toma más parecido al año que al semestre. Entonces, pues muchas felicitaciones, porque además se ve que tuviste que cumplir, o sea, a profundizar en un montón de conocimientos y luego ponerlos en práctica.
Claro, sí.
Muchas felicidades por eso.
Gracias.
Mi pregunta uno va, me queda claro que en tu scope no estaba construir y diseñar digamos, el sistema.
Ajá.
Sin embargo, tus resultados arrancan con el dispositivo. Exactamente. Entonces, no sé si con esas o con las figuras que después llamaste 11, ¿hay alguna forma de tener
Ajá.
tu dispositivo y saber de estas imágenes y ópticas y de SEM si logramos, me incluí, si lograste tener un quantum dot en el sistema o únicamente es a través del experimento que corriste que te das cuenta si funcionó o no? O sea, porque según yo tenías
61.
61, pero al final 23
Sí,
fueron
correcto.
las que sí. O sea, ese proceso lo pueden ver a través del SEM y las imágenes ópticas o solo pasando por todo el proceso de experimentación. Tal vez nos contás un poco de esa primera parte.
Ok, aquí lo que pasa es que, bueno, acá está un zoom progresivo de la muestra. Entonces, digamos, primero se fabrica la muestra y, como mencioné al puro principio, los puntos cuánticos se generan aleatoriamente y después se hace la escritura litográfica de todas las estructuras. Entonces, digamos, acá se ve como el mapita donde uno define cuadritos donde uno va a fabricar las estructuras, los CVGs, digamos. Entonces, lo que uno hace es que en cada cuadrito hace esta imagen SEM y busca si hay puntos cuánticos. En este caso, aquí se puede ver que hay un punto amarillo. Aquí en el puro centro hay otro, pero pues se ve pequeño. Y digamos, lo que normalmente se ven es estos puntos amarillos. Entonces ahí es donde uno dice, aquí hay un punto cuántico. Entonces, alrededor de ese punto cuántico es que se fabrican las estructuras.
Súper. Entonces, ¿era posible, digamos, como descartar un dispositivo si del todo no te parecía esa imagen
Exacto,
amarilla
sí.
antes de pasar por todo el proceso de experimentación? Digamos,
Exactamente.
decir, "Ay, no tiene eficiencia cero, por lo tanto, pues ahí no había".
Claro, sí. Y digamos, la razón de por qué se pude analizar 23 de las 61 fue porque, bueno, algunas de las estructuras se escribieron incorrectamente, entonces la que le correspondía a una se le puso a otra y pues eso pasó con varias. Y el resto fue porque para las mediciones de las series de potencia y de polarización, la emisión tenía demasiado ruido, entonces no se podía identificar bien las líneas espectrales. Y pues si no podía identificar principalmente los complejos excitónicos, los más bajos, no podía calcular la eficiencia de extracción. Entonces, al menos correctamente.
Y tal vez como para cerrar esta y después paso a Juan Carlos, para que vayamos intercambiando. eh, ¿A qué se debía el ruido de esas? O sea, ¿por qué algunas tienen ruido y otras no? O sea,
Ajá.
sí pueden determinarlo. ¿O es algo que sucede? Que a veces experimentalmente
Sí,
pasa.
sí, es algo demasiado experimental y uno puede sacar hipótesis de por qué es, que bueno, puede ser también por esto que mencionaba el profesor de que no está perfectamente centrado en la estructura, porque, ¿verdad? Estos son 10 micrómetros de la estructura que más o menos mide 8 y el punto cuántico lo que mide son 20 nanómetros. Entonces, hay mucho margen de error para que no esté centrado y entonces por eso es que puede que haya tanto ruido.
Bueno, igual felicitarte, Natalia, un trabajo muy arduo. Eh, me cuesta, digamos, me sorprende mucho que un trabajo tan grande se pueda hacer en un semestre, ¿verdad? Felicitaciones. Si usted me hubiera dicho que era de un año, le hubiera creído perfectamente.
Sí.
Considerando el conjunto de todos los resultados, ¿diría usted que estas fuentes están más limitadas por la física intrínseca o propia de los puntos cuánticos o por aspectos tecnológicos del dispositivo o de las mediciones?
Ok, pues yo diría que como notamos que el parpadeo y los procesos de recaptura fueron tan dominantes, pues yo diría que las limitaciones son más por la física y las propiedades cuánticas ópticas de las fuentes, de los puntos cuánticos. Porque, bueno, en realidad las estructuras, los CVGs, en realidad no afectan estas propiedades cuánticas ópticas de los puntos cuánticos, sino que solamente tratan de optimizar la emisión que de por sí van a dar.
Y a partir de los resultados que obtuviste para G2, ¿cómo evalúas la calidad real de las fuentes estudiadas frente a los requisitos prácticos de comunicación cuántica?
Ok. Sobre el G2, bueno, para ya tener una fuente funcional que se pueda aplicar directamente a comunicaciones cuánticas, pues lo que buscamos es que sean seguras basándose en el hecho de que emiten un solo fotón. Entonces, pues en realidad necesitamos que la pureza sea lo más alta posible. Y aquí la más alta que tuvimos fue de 98.7%, que sí está bastante bien, está dentro del rango de algunos estudios recientes que se han hecho, pero pues no llega a ser suficiente para poder aplicarlo ahora sí a aplicaciones reales. Por eso es que, pues como mencioné al final, se necesita seguir haciendo estudios sobre, bueno, continuar la caracterización de las fuentes, que pues había otras características que por tiempo no podía incluir pues, en el proyecto, pero, pero sí, o sea, vamos en camino, pero todavía no se llega al objetivo.
Ok, según lo que pude entender de tu trabajo, las que son, digamos, a ver, tengo numeradas. Ah, bueno, ahí está. Las
Ajá,
figuras 18, 19 y 20 están relacionadas, explican
correcto.
una historia en conjunto.
Sí,
Y por cosas de tiempo, me parece que aunque estuvo, es el momento de que nos contes ya, sin,
ok.
sin el cronómetro encima, exactamente la historia que cuentan juntas y a qué llegan en tu trabajo.
Ok, bueno, entonces digamos, esta son los histogramas de los datos crudos, digamos, de las mediciones de HBT, que es lo que se hace para sacar el G2. Entonces, bueno, nosotros dejamos el detector corriendo, él tira este histograma y después con los archivos de datos que él nos da, lo que calculamos ya es el valor del G2 y las incertidumbres y todo. Entonces, así es como están relacionadas.
Y entonces, si querés, ahora sí, con esta relación clara, nos contás lo que se concluye de los dispositivos que elegiste para hacer esas mediciones.
Ok, bueno, entonces sí, lo que concluimos con estas estructuras en particulares, esta muestra, es que sí es funcional, se puede usar para lo que se busca, pero no es óptima, o sea, no es lo ideal que queremos. Entonces, pues sí, con una eficiencia del 98-90% es válido, se puede utilizar, pero verdad, no va a ser lo mejor.
Como recomendación, ¿qué acciones concretas sugerirías para futuros trabajos con el objetivo de lograr simultáneamente alta pureza y también mayor eficacia de extracción?
Ok, bueno, esto en particular tiene más que ver con la fabricación que con el estudio en sí que hicimos aquí. Que bueno, la idea de hacer estas mediciones es que el equipo que fabrica las muestras tenga más datos, pueda reconocer patrones, y ellos hacen cualquier cantidad de muestras, entonces con los estudios de cada una van reconociendo, ok, qué características son las mejores y juntarlas y con eso ir mejorando las características para que van a mejorar pues la extracción de fotones y la pureza. Ahora, sí hay ciertos aspectos del estudio que son difíciles, son complicados de mejorar. Por ejemplo, principalmente los problemas vienen con el montaje óptico, porque, digamos, tenemos para poder enfocar la emisión a la fibra óptica, tenemos que manualmente mover espejos para, ¿verdad?, optimizar el ángulo de entrada a la fibra óptica, que eso, ¿verdad?, es complicado. Entonces, tenemos que primero optimizar la entrada del láser a una fibra óptica que viene antes y aquí sale acá. Después hay que optimizar, por ejemplo, el ángulo de la placa de media onda, porque si uno la gira un poquito, se va a dañar la emisión. Entonces, sí, esas son cosas que se pueden mejorar, pero igual son complicadas. Hay que darle mucho tiempo y en eso, de hecho, estuvimos un montón de tiempo mejorando el montaje.
Ok, gracias Natalia y Juan Carlos por las preguntas y Natalia por sus respuestas. Vamos brevemente a retirarnos del auditorio para que el jurado delibere y se coloque la nota. Sí. ¿Pero en qué momento? Es que no sé. Bueno, está bien. Yo no sé, no estaba preparada para esto. Hola, hello everyone, welcome back. Bienvenidos nuevamente a todos al auditorio. El jurado, perdón, ya estamos en línea, ¿verdad? El jurado se tomó un tiempo para evaluar la calidad de la presentación y las respuestas de Natalia. Parece que fueron muy satisfactorias y es para mí un honor presentar que la nota obtenida es un 100 con mención honorífica. And for our guests, the grade is 100, the best grade of all. And it has honors in her grade as well because she did an amazing presentation. Entonces, muchas gracias a las personas participantes. Thank you very much to our guests in Germany. And Natalia, congratulations. You did an amazing work. And we hope the best for you and your academic career. Give her an applause and we will finish the defense.
Thank you so much.
Congratulations, Natalia.
Oh, thank you.
Very well done.
Bueno, muchas gracias, estimado público. Vamos a seguir con las defensas, entonces, y vamos a dar